In the next chapters, we will see different kinds of graphs in order to display different kinds of variables. And we will start here in chapter 10 with categorical variables. We often see tables in articles and research reports. Tables are very good ways to describe variables. They can be categorical, they can be quantitative, it can be just describing one variable or displaying a correlation between variables. You have regular tables, two-way tables, three-way tables, we'll see that. But tables are not the best way to give a very quick overview about how variables are distributed. Graphs are better for that. Here, for example, you have a very simple table showing different blood types in the Canadian population. The left column shows the blood types themselves, the four. The column in the middle shows rates in the population for each of the four blood types, and the column on the right shows counts instead of rates. The data showed in the preceding table would be easier to see in one glimpse if it was illustrated in a graph. And since we have here one categorical variable, your blood type, O, A, B, or AB, it is okay to show it in a pie chart, because pie charts are what we use to illustrate categorical variables that are part of a whole. So here, each member of the Canadian population has only one blood type, and no one has no blood type. So the whole population is represented here, and we have only four blood types. So a pie chart would be a very good way to illustrate this categorical variable. Pie charts are not very good when it's time to illustrate a variable that can be expressed in many different ways. If I had 32 blood types to illustrate instead of 4, that would be illustrated in a very cluttered pie chart. So it is not good here. The example you see here in the image is an illustration of that. When there are too many possibilities for a variable, pie charts are not good, and maybe here it would be better to keep the table. Bar graphs are another way to display categorical variables. Bar graphs are mostly used to compare several quantities. So you know that already. The higher the bar, the more subjects you have in each category. Clustered bar graphs are very interesting, and you will see them again at the very end of the semester. But for now, let's say that they're interesting because they can show the correlation between variables. So each variable can be divided into some subgroups. For example, here I have two variables illustrated in this clustered bar graph. This is a population of individuals. I have males and females, males in pink and females in green. And I have hair color, 4 possibilities. So these two variables are both categorical, so it's okay to use a clustered bar graph here. So for each of the hair color, I have how many men and women are represented. And you can already see very, very quick a correlation here. More females have blonde hair, and only males have red hair. There is a correlation here between the male gender and red hair, and more males have brown and black hair. This second example of a clustered bar graph shows the correlation between the type of cars and how popular they are in 3 continents. So the color of the bar indicates the continent, either Asia, Europe, and USA, North America. and each cluster indicates a type of car. So very quick, you can see in this table that in Europe, people have less SUVs and more sports cars. And trucks are absolutely not popular. And only in Asia, there are hybrid vehicles. An important reminder here, bar graphs and pie charts are there to illustrate categorical variables only. And a categorical variable is not a number, it is a category. Your occupation, your gender, etc. An important detail as well. Bar graphs and pie charts can illustrate different things. Bar charts compare separate quantities, so they can be used for nearly all categorical variables. But pie charts, if you want to use a pie chart, you need a variable that has some characteristics. First, your quantities that you illustrate in your pie chart, they can be counts, they can be rates, but they need to be parts of a whole. For my blood groups, for example, we're part of a whole. Everyone in the Canadian population has one blood group. Here, in this example, you have the pie preference for, let's say, it's the Canadian population as well. So you have 5 possible choices here. Each person in the population has only one favorite pie flavor. And it's part of a whole. These pie flavors represent the whole population. Also, if you want to illustrate a categorical variable with a pie chart, each individual must fall into one category and one category only. I cannot have 2 blood groups at once. I have only one blood group. I cannot have 2 favorite pie flavors. Only one flavor is my favorite. So these 2 variables can be represented with pie charts. And there's a very important detail about pie charts and bar graphs. Not all bar graphs can be turned into pie charts. If you look carefully at these 2 bar graphs, only one can be. The one on the left. The bar graph on the left represents how many patients in a hospital. There is a population of 50 patients. How many patients you have for each blood type. So these patients are part of whole, are part of the full population, and each one has only one blood type. So you can turn it into a pie chart. That's absolutely correct. But the bar graph on the right cannot be turned into a pie chart because it does not represent parts of a whole. It compares different amounts of dollars collected in different years. So each bar represents a year, and the height of the bar represents how many dollars were collected. It's impossible to turn that into a pie chart because you do not represent part of a whole population. So there's only one possibility here, showing this data with a bar graph. A few words about line graphs to finish this. Line graphs are not necessarily linked with categorical variables. They can represent quantitative variables, and line graphs are there to display change over time. So they are there to represent only one variable. They can represent 2 variables, but you need 2 lines in your line graph. So each line is there to display one variable, and each line displays how this variable changes through time. A good example here that you see very often in the media is the weather forecast for the next 14 days. So on the y-axis, on the vertical axis, you have the number of degrees, Celsius degrees, And on the x-axis, the horizontal axis, you have how the degrees change over time. So very quickly, if you look at this graph, you see that the temperature is going down in the next 14 days. The forecast is like that. I could express these variables into a table, but showing it in a graph gives a very quick and precise overview. So again, time goes on the x-axis, the horizontal axis, and the variable you measure goes on the y-axis. For example, in this line graph here, you see the progression of the coronavirus infections for the last 6 months, from January to June. And you see two lines, the green one representing United States and the white one representing Europe. So you can compare these two variables very quickly, how they have changed over time if you look at this line graph. Be careful when you see a line graph or when you create a line graph, because they can be easily manipulated. Sometimes people who express data in line graphs have precise agenda, so they will manipulate the axis in order to make their data look differently. For example, the line graph on the left here and on the right represent the exact same data and the same numbers. You have on the y-axis the number of unmarried couples in thousands, probably in United States, and the x-axis is showing how the number of unmarried couples have progressed through time from 1980 to year 2000. So the line graph on the left shows a x-axis that is very spread out, and the graph on the right shows an x-axis that is very tight. So you see here that the same data gives very different feelings. On the left, you see that very quickly and you say, oh, the numbers are not rising so quickly. And if you look at the same data on the right, you will see, oh my goodness, that's terrible. It's rising so much. So here they represent unmarried couples, but they can represent anything. So you can manipulate what people think depending on how you build your line graph. Be careful. And also, very important in line graphs, and these here, even if they're manipulated, they're correct on that way. The x-axis, the one showing time, has to be equally divided. That's important. So each subdivision of the x-axis must show the same number of years, months, days, or seconds, or whatever you're calculating, but your x-axis must be evenly separated.